Dear students, let us discuss SN2 mechanism today. The full form of SN2 is substitution, nucleophilic, bimolecular reaction. Bimolecular means the order of the reaction is 2. When you shall be doing chemical kinetics, you must be taught what is the order of the reaction. Here also I'll try to explain a little bit. In this type of reaction mechanism, the attack of the nucleophile and the leaving group halogen occurs simultaneously. The incoming nucleophile always attack from the opposite side with respect to the halogen. For optically active haloalkanes, the reaction always occurs by inversion of configuration. The reaction is governed by steric hindrance. By steric hindrance, what we mean? The crowding around the carbon. Smaller the group attached to the carbon where the nucleophile is supposed to attack, better is the possibility for the attack. If the groups attached to the carbon are bulky, then the attack becomes difficult. So less is the steric hindrance, more is the possibility of SN2 mechanism. So the reaction is favored in a non-polar solvent because here no carbocation, no carbon ions are forming. That's why the reaction is favored in a non-polar solvent. Now, as you know, it is a one-step reaction, so we call it elementary reaction. And in one-step reaction, both the haloalkane as well as the nucleophile are involved. So when we calculate the order of the reaction, it depends on the concentration of haloalkane as well as on the concentration of the nucleophile. Hence, order of the reaction becomes 2. Now, let us try to understand this reaction mechanism. I have taken the same example as we have discussed for SN1 mechanism. That is, chloromethane reacts with sodium hydroxide aqueous to give you methanol and sodium chloride. Now here, as you see, methanol, if I have written the structure of chloromethane, you can see this carbon is attached to 3 hydrogens and 1 chlorine. Now I have placed the chlorine on the right. So the nucleophile OH minus cannot attack from right, it has to attack from left. Okay, because both OH minus and chlorine, they are electron rich. So if they approach from the same side, if they are on the same side, they will suffer a lot of electronic repulsion and OH minus won't be able to approach the carbon. Now why does the OH minus approach the carbon? Because because of the chlorine here, which is causing a dipole moment, the carbon out here is partially positive, and because of this partial positive charge on the carbon, the OH minus is attacking from the opposite end. So during the course of reaction, a transition state is formed. Usually transition states are not having very long life, very short life period, and we represent them by a square bracket. So in this transition state, what is happening? You see the bond between HO and C is partially forming, and the bond between carbon and chlorine is partially breaking, because carbon cannot have more than 4 bonds because its valency is 4. So if OH attacks, a partial bond tends to form. Here you can see as if carbon is having 5 bonds. So here the chlorine has to go because we are doing substitution of chlorine, and the product which we get is alcohol. Now the question is, if the carbon out here is optically active. By optically active, what we mean? If all the 4 groups attached to the carbon are different. In this present case, it is not optically active because it has same hydrogens more than once. If all the 4 groups are different here, then the product which will be formed, that also will be optically active, and the product is said to have formed by inversion of configuration. So remember one more thing, by inversion of configuration, it doesn't mean if this is dextrorotatory, the other one will become levorotatory, nothing like that. Okay. Optical rotation is totally based on experimental evidences. Looking at the structure, we will never be able to predict whether the compound is dextrorotatory or levorotatory. Only thing which we can predict by looking at the structure is whether the compound is optically active or not. In this present case, the compound is not optically active because the groups attached to the carbon are not all different. They are more or less same. Now, how do we calculate the rate of the reaction? You know that the rate of the reaction is governed by the slowest step. But since it is a one-step reaction, there is no question of slow step or first step. So, what happens here? Both the nucleophile and the haloalkane are equally responsible for carrying out the reaction. As a result, the order of the reaction, which will be calculated by using this formula, R equals K into CH3, concentration of CH3Cl and concentration of OH minus. Now the power of the concentration terms are both 1. So order of the reaction will be 1 plus 1 equal to 2. And that is why we call it a second order reaction. So that's how we name it as SN2 reaction. Now how the order of the reaction will vary? The order of the reaction will vary. As I said, the governing factor is steric hindrance. So among all the alkyl groups, you know, methyl group is the smallest. The carbon is having smallest group attached to it, that is hydrogen. So methyl alkyl groups haloalkanes containing methyl group, the probability of reaction is maximum. As the bulkiness of the groups attached are increasing, the tendency of undergoing SN2 mechanism will decrease. So that's all about SN2 reaction. During exams, if reaction mechanisms are asked, you need to check what type of haloalkane is given to you. If the haloalkane is methyl or primary, it has more probability of undergoing SN2 mechanism. If the haloalkane is secondary or tertiary, it has more tendency to undergo SN1 mechanism.